अनिमित का वीडियो कैसे प्ले करेंगे? ये वीडियोस पर डालना सर, एक वीडियो ही प्ले होना है बीच में, वो भी ऐड करो।
ये तो आज बताया जा रहा है अभी।
मुझे लगा था कि ऐसे
नहीं होता है।
और
आपकी ईमेल आईडी है?
ज्वाइन नहीं हो यहाँ से देख
Hello, can you hear me?
Yes, sir, we can hear you.
Okay. And my video is also visible.
Yeah, sir, it is visible.
Okay. So it's almost time. Is there anybody to say something, or I have to start the lecture directly?
Good morning, all.
Shukla sir, am I audible?
Yes, yes. Now, am I audible to all of you? Abhin?
Just a minute, sir. सर एक बार बोलिए.
Abhin, can you hear me? Hello? Abhin?
Yeah, we can hear you. Yeah.
Yes, yes. Abhin, can you hear me? Am I audible to all of you?
Yes, sir.
Abhin?
Yes, sir, you are audible. Just a minute, sir. सर एक बार बोलिए.
Abhin, can you hear me?
Yes, sir.
We can hear you.
Abhin, are you going to start? Abhin?
Yes, sir, you are audible.
It doesn't matter. 5 minutes में start.
चलो start ठीक है क्या कैमरा ऑन है.
Deepika? Deepika?
चलो.
Abhin, are you going to start?
Yes, sir.
इसमें correct नहीं है.
Deepika, am I audible?
उसमें lag आ.
Abhin, am I audible? Abhin? Deepika?
Yes, sir. उसमें lag आ. आपके पास lead नहीं.
Abhin? Am I audible?
इसका lead. इसका पता नहीं. इसका lead दो. सर वो कैमरा माइक दो. इसका ये कनेक्ट करना पड़ेगा. इसको फिर मुझे ज्वाइन करना पड़ेगा. मैम बहुत ज्यादा lag आ.
आप 5 मिनट बाद लाएं.
मैं अब बोल रहा हूँ तो उसमें 5 मिनट बाद आएगा.
And ये केवल कि आप ये स्क्रीन चलाना चाहते हैं. बस उसको आप
Shukla sir.
Yes. Am I audible?
Yeah, audible sir.
Okay. Thank you.
सर आप उसका ना स्पीकर सही वो 5 मिनट बाद आ रहा है उसकी वजह से डिस्टर्बेंस होता है
ये वीडियो
We'll start from speaker will start again.
लास्ट में इनकी लेक्चर के बाद प्ले कर देंगे लास्ट में
MK sir, am I audible?
Yes, yes, you are audible. Is my
Quiet.
Logic will take you from A to B. Imagination will take you everywhere, said Albert Einstein. As students of a subject that is dictated through logic and rationality, I believe it is only fair that we take some time to channel our creativity and imagination. A very good morning to everyone present here. A warm welcome to our esteemed principal, Professor C. Sheila Reddy, our chief guest, Professor Sumesh Kumar from IIT Kharagpur, respected teachers of the statistics department, and my peers. I extend a very warm welcome to our chief guest, Professor Sumesh Kumar from the Department of Mathematics, IIT Kharagpur, who has set a benchmark for multi-hyphenated scales in the field of statistics. He has published numerous research papers, the main area of his research being statistical decision theory and inference. He has been the recipient of Bharat Jyoti Award and the Platinum Jubilee Lecture Award. As young and budding statisticians, we're sure your words of wisdom today will be of great aid to us going forward, sir. The Statistics Association is proud to be organizing another edition of the annual Departmental Fest simulation. The Statistics Association has enjoyed great success for the current academic year 2021-22, having organized numerous webinars across domains and celebrated key moments for the department. After having spent close to 2 years at home, desk-ridden, we are fortunate to have put together the 2-day event. I would like to thank all those involved in making this event a reality. The core members, General Secretary Raghav Kamra, Treasurer Hemant Yadav, and Shruti Vora, our Vice President, whose contributions were truly instrumental for the organization of this event. I would also like to wish luck and, more importantly, thank our event heads for planning a variety of creative and engaging events under the able guidance of our respected teachers. I feel privileged to open the event on behalf of both the Statistics Department and the Association. So without much further ado, let's commence Simulation 2022. I would now like to pass the metaphorical mic to Shruti. Thank you.
Thank you so much, Abhin, for opening the event. Now I would like to call upon our senior professor, Shukla sir, to say a few words. Over to you, sir.
good morning, all. Respected principal, madam, dear colleagues, and my dear students. I, on behalf of the whole statistics fraternity at the Sri Venkateswara College, once again welcome you all to the Inter-College Festival Simulation 2022. Today, we are indeed quite honored to have with us Professor Sumesh Kumar from Department of Mathematics, IIT Kharagpur. So it is my special privilege to welcome you, sir, to Sri Venkateswara College. The Department of Statistics, Sri Venkateswara College, University of Delhi, was established in the year 1977. The department offers undergraduate and postgraduate course in statistics. So this is one of the oldest department in the University of Delhi. Currently, there are 10 faculty members who remains devoted in nurturing knowledge, quotient, and proper learning of our students. The department has earned for itself an excellent reputation in teaching and research with specialization in statistical inference, design of experiment, survey sampling, linear models, econometrics, stochastic process, and other applied areas of statistics. The department has proud history, and most of the faculty members in other due colleges of statistics department are the product of this great institution. Simulation 2022 is an inter-college festival of Department of Statistics. Almost all the colleges of due are generally take part in this festival and showcase their talents. My special thanks to my young colleagues, Deepika, Tanuja, Kanika, Parul, Chetan, Ramesh, Alok, and to my students, particularly for arranging this festival. So after a gap of 2 years due to COVID-19, today's lecture is an effort to get some knowledge on recent works in statistics and data science, which is the prominent field today for a student of statistics. Finally, I can say it will definitely put some positive impact on my young statisticians. Thank you all. I wish all the best for this success of this festival, Simulation 2022. Over to Avin.
Thank you so much, sir, for being our inspiration and constantly supporting and guiding us. Now, I would like to move on to the much awaited speaker session of the event. I hereby invite our honorable chief guest, Professor Sumesh Kumar from IIT Kharagpur for his speaker session, History and Recent Works in Statistics and Data Science. Over to you, sir.
First of all, I would like to thank the organizers of simulation and the administrators of the Venkateshwar College for inviting me as the chief guest for this program and to share my thoughts on statistics and data science to all the participants of this inter-college festival simulation. It is certainly very nice to interact with the young students because they are the ones who will take forward the research and the teaching and also the practice of statistics to the world. I can see, I think one or two students I can recognize. I can see the screen of the system administrator. I think, is it Tanuja there? Yeah, I think so. Yeah, probably I have met her in some conference, so it's very good to see her. And okay, so let me start with a little, before I share my slide, I will just like to say a few things. One is that statistics is no longer a appendix or supporting subject of anything. Actually, statistics is now the key subject. So anybody in any branch of science, engineering, humanities, economics, anyway, management or medical, if he has to come to a certain conclusion to make a policy for something or to plan for something, statistics is a must for that. And for that, actually, the role of students of statistics is now very important because they should not think something that, oh, they will, if they do statistics, they will get some job. It's not just getting a job. It's actually helping the society in a larger objective. So, for example, you might have noted in the this pandemic period, you saw from the day one you started getting the data that, okay, in this country it started, how many patients are there, how many people recovered, what is the mortality rate, how many people get serious. Everywhere it was a flood of data. And from the flood of the data, immediately there were scientists, the statisticians, for example, a lot of statisticians from India as well as from Oxford University, you saw from the Johns Hopkins University and so on. They started analyzing that data and giving certain predictions like how it will peak up, how it will go down, how many expected number of hospitalizations will be there, what will be the resources required. And then first wave, second wave, third wave. Like in India, of course, we saw that it was much more, you can say, statistical model was really fitting nicely in the Indian situation, which was not the case in other countries. So it may be that there was a lot of administrative steps were taken in India. So maybe due to that, the curves were much nice. I mean, I think all of you can see the websites of the government or in the worldometer, etc. And you can look at the curves, where in the first phase we had a very fat-tailed, or you can say heavy-tailed distribution. In the second one, we had something like a very steep, something like a T distribution. And in the third phase, we had very, very steep thing. And of course, now there is some prediction again from IIT Kanpur statistics people that there will be some fourth wave, which may or may not be there. And certainly this is only guideline because it tells you how to take care of the future. I mean, the government can prepare itself so that maybe the fourth wave effect will be less. I mean, you might have already noted that the third wave effect was less. So I think it is just an example. As an introduction, I wanted to tell that the role of a statistician is paramount in today's, you can say, today's world. Again, you can see that there is immediately after COVID, something else has started. That is the Russia-Ukraine war. And again, you can see there is an enormous effect on the economy. And every day you can see certain analysis by the economists and by the statisticians about the GDP growth, about the prices of the essential items, about the supply chain of various essential items, and also the human catastrophe that that is taking place. So the economic costs and of course the social costs which are going to happen. Again, it is a role of a statistician which is paramount here. So now let me start sharing my screen. And actually, I have prepared this talk because whenever the student body is there, I would like to give them a historical perspective about the development of the statistics. And then plus I say that, okay, we have also done research work in these areas. So what are the current important research areas? So I would like to say those things. Let me share my screen now. Okay, so can you see my screen now?
Yes, sir, we can.
Okay, so let me start the presentation. So these are the terminologies that are coming to everybody. So something called data, probability, statistics, data science, and people use them synonymously. Okay, I mean, if you say data science, so somebody will say it is statistics, or if you say probability, then somebody will say it's data science, and so on. So people have different understanding. So I'd like to just give a brief hold on each of them. What are these things referring to? So the term data, that is quite old. There are instructions for collecting data in the area of agriculture, for example. How many workers are there? What is the crime data? That means how many crimes do take place, and about, of course, business, commerce, etc. So even if you look at the version of Kautilya's Arthashastra, which is present day available, you can look at it. There are a lot of instructions about the data there. And later on, in the Gupta dynasty, Chola dynasty, Chalukya empires, ancient Rome, Greece, and then many other countries in Europe like France, England, Netherlands, Denmark, etc. There are data available. So references to the data collection by various governments are available. So it is evident that in order to draw meaningful conclusions from any experiments in physical, chemical sciences, engineering, biosciences, clinical trials, medicine, psychology, genetics, agriculture, economics, or social sciences, one needs to employ statistical tools. Initially, the term statistics refer to data and collection of the data. However, currently the statistics refers to planning and design of experiments, sampling, collection of data, methods for modeling and analyzing data, and finally drawing meaningful inferences from it to enable individuals, organizations, governments to formulate policies. Statistical methods are dependent on probability and distributions. the increasing use of statistics has led to the development of methods which use advanced computational techniques to analyze complex problems. Because what has happened, for example, you look at the COVID data itself. So you have around 200 countries in the world. In each country, there are so many states or the provinces or the districts, and everywhere the data is coming. And then you have the data has to be classified for various things. For example, people getting the disease, they get elementary symptoms, they get serious symptoms, they need hospitalization, or they lead to mortality. All of these things, I mean, lead to enormous data coming from 200 countries of the world. So unless you use some advanced computational methodologies, you cannot do it. So like if you really want to just apply, say, a regression method or a prediction model or just some estimation, then you will need thousands of statisticians doing that kind of thing. But if you want some sort of central policies like World Health Organization or United Nations organizations or governments of large countries like India, you cannot have thousands of statisticians or people doing the work. So you need that the data comes to some centralized facility, and then certain computational methods should be used. So any person who specializes in these are called data scientists. Okay, so basically data scientist is a statistician, and that means he is actually going to use statistical methods, but he will apply advanced computational techniques to actually get to reduce the data and then get certain things. So nowadays in organizations, you have recruiters who look for someone who is a data scientist. So I mean, this is a little humorous kind of statement that a person who is better at statistics than any software engineer and better at software engineering than any statistician. So such a person can be called a data scientist. Again, there are a lot of confusion, like people use data analyst and data scientist in synonymous words. But what is data analytics? Data analytics refers to techniques and methodologies to analyze, interpret data, and aid in decision making for the practitioner in his or her domain. But for doing any statistics or any statistical methods or any data analysis, the foundation is probability. However, the term of probability has also been being used for a long time, and it was understood even in the ancient times that there is uncertainty. So for example, in the gambling games, you have references to the game of dice, that is that Chaucer or Chopard, etc. So you have the stories of Nal Damayanti or Mahabharat, or in Satyabhama Jambavati, there was a game of dice and so on. But later on, it has been realized. So initially, what was thought that people thought that, okay, the physical theories or the chemical theories or other theories have not been developed sufficiently, and therefore uncertainty cannot be understood, that why there is uncertainty, and therefore probability method should be used. However, in the 20th century, it was realized that no matter what unification of the physics you do, or what chemical theory or what genetic evolution theory is developed, uncertainty cannot be removed. That means everywhere it will be there. So it is realized that uncertainty is present in almost all phenomena in real life. So it is not by that it is due to a lack of knowledge or due to lack of scientific development. Whatever scientific development we do or whatever other things we do, uncertainty will remain there. So one has to model the uncertainty and then make the predictions which will come good. So for example, I am just again referring to the COVID because that is the one which we went through in the last 2 years. So how do you say that, okay, the disease phase has gone or something? Because there will be always some people who will be getting the disease. There will be always some mortalities also. But when the disease phase is gone, how do you say? When you find that the R naught value that has become much less than 1. That means the rate of infection has gone down. So the disease may still be there because R naught value will be something. It may be 0.01 or something. But when it was greater than 1, that means every day when the next day's data is coming, then you will have more number of patients than the previous day. When R naught value became less than 1, it because then it led to the reduction. But now the R naught value has come down substantially, so that means the rate of infection has gone down. So it does not mean that the disease has gone down, but this is statistical modeling here. Okay. So I'm just giving these references, I mean, of uncertainty in the events, which we all know. As students of statistics, you come across all these terminologies. So what is the weather conditions? So we all talk about the climate change and other kind of things, and day-to-day weather also. So what is the weather? It is uncertain. A child born today, what would be his height when he or she becomes an adult? That cannot be predicted. Even when you have all the things fixed, for example, you say that, okay, the parents are 6 feet tall and they are from healthy family and they have this much of money so that they can spend substantial amount on his health. Even then, how much height he will achieve cannot be predicted in advance. The amount of crop area, the quality of the seeds, the quality of the fertilizers, whether for chemical or organic fertilizers, given all these things, you cannot predict how much food grain production will be there. Exact amount of the food grain production cannot be said. You can only say that it will be within this range or something like that. How much a person's total life would be, it cannot be told in advance. So whether a person will live 80 years or he will live up to 60 years or he will live up to 55 years, you cannot tell in advance. During a cyclone or super cyclone, what would be the height of the storm surge? So we make models where we give certain ranges, but we cannot tell exactly that this will be the height of the storm surge. Persons get a disease, so you get fever or you get say stomach upset or you get some other kind of disease, and you go to a medical doctor and get some medicine. How much time it will take to get cured? Although maybe there are 10 persons getting the same disease, they go to the same doctor and get the same medicine, but the time taken to get cured will be different. Somebody may get cured in 1 day, somebody may get cured in 7 days, and so on. If you consider the day-to-day systolic and diastolic blood pressure of a person at any given point of the day, it will vary. It cannot be fixed that it will always be 120 by 80. Sometimes it may be 122 by 80. Sometimes it may be 130 by 90, and so on. If a test is conducted, say in your probability class or in your inference class, how many students will score more than 75% of the marks? It cannot be said in advance. The total life of an equipment, for example, your mobile phone, your laptop charger, your battery, your all the equipments that you are using now. For example, you have a camera, you have a speaker, you have a headphone, and so on. What is the total life of that? So although all the products may be from the same company of the same quality, but even then the total life differs. So I just mentioned here that uncertainty terminology was known long back, but the modern probability, the development of the modern theory, it is started in the Middle Europe. So there was a person called Cardano. He was sort of an all-rounder. He was a physician and a mathematician, and he is credited to be the first person to consider a systematic study of probability concepts. He lived from 1501 to 1575. However, his work was published long after he died. It was actually published in 1663, and it is actually he kept a diary, and that diary was published as a book. So it's a 15-page book consisting of 32 small chapters, and the title is the Liber de Ludo Ele, that is the book on games of chance. So he was an Italian. So that time, actually, if you look at the medieval Europe, so there used to be gambling dens, casinos, where the games of dice, games of roulette wheel, the games of cards, etc. were being played. So anyway, I mean, in the society, there will be a lot of people who will be actually gambling. So this person was a gambler, and therefore he wanted to know that how can he maximize the probability of this winning. And therefore, he started to think in a scientific way. So this book actually contains rules for games as well as an advice how to protect oneself against cheating. Cardano, he discussed the methods of cheating that include false dice, marked cards, palming cards, tilted gambling tables, and the use of tipsets. So as you can understand, since he was a gambler, his interest in the probability originated from this only. So there is an interesting book written by Austin Orr, Cardano, the Gambling Scholar. It is published by Princeton University Press. So nowadays, of course, one can access all the books through Amazon and all that. So if those who are interested, you can actually buy the book and read it. And one of the problems that he considered, I'm just giving an example that what is the difficulty in starting a new scientific theory? Since before that, there was no probability theory, therefore any question would look very difficult. Nowadays, you just write an event and then you consider a very straightforward methodology by the classical definition or by the relative frequency definition, apply the rules of probability and get the answer. But how much difficult it was with Cardano, you can look at from the answer to this question. How many throws of a fair dice do we need in order to have an even chance of at least 1/6? That means what is how many throws of a dice are required so that probability of at least 1/6 is greater than half. Okay, so this looks a very simple questions currently. I have written here the solution like you will do it for any BSc statistics student. That if I define A to be the event in which a 6 shows in one throw of a dice, then probability of A is 1/6 if we are considering the dice to be a fair. Now, assuming the independence of the throws, so probability of a 6 shows it at least once in n throws is 1 minus the probability that there is no 6 in n throws. Now, in one throw of a dice, there is no 6, that is 5/6. So in throws, it becomes 5/6 to the power n. So the required probability becomes 1 minus 5/6 to the power n. Now we want it to be greater than half. So minimum value of that n will be n is greater than or equal to 4. But even this answer by the Cardano's argument, he got the answer to be 3. So you can understand the difficulty in initiating a theory, in starting a new theory of anything. So anyway, he was the first one to give a formal, you can say, treatment to the problems of probability. The theory of probability actually originated in the middle of 17th century, and I have put the names of Fermat, Pascal, Heinz, and James Bernoulli. They were all almost contemporaries. They all lived in the, basically you can say 17th century. And they had a lot of exchange of letters among themselves, especially Fermat and Pascal. And that led to the formal, you can say, formalization of the concepts of probability theory. Actually, there is a book by Anthony Arnold and Pierre Nicole. The title of the book is Law Logic. So it's a French book actually. And if you translate it into the English, it becomes Port Royal Logic. And in this book, actually, the term probability itself was used as a numerical measure for the first time. I just put photographs of these people from Wikipedia pages just to show you. After this, you can say, elementary discussions about the concepts of the probability, a formalization took place. And I am putting the names of the few people who can be considered as the pioneers of the definitions which we teach to our students of BSc, MSc statistics. So these are the names: Laplace and von Mises. So the first definition that you do in your school, that if I want to calculate the probability that a 6 will come if a fair dice is thrown, then you say it is 1 by 6. So what you do, you consider that each of 1, 2, 3, 4, 5, 6 outcomes are equally likely. So that's why we call it a fair dice. And then you look at the favorable event. What is the favorable event? That is occurrence of 6. So that is 1 out of 6. So you assign the probability 1 by 6. This classical definition was actually given by Laplace. Of course, before Laplace, I have mentioned the names of some of the people, that is Pascal, Fermat, and so on. So they all actually use such things, but formal definition was given by Laplace in his famous book, Theory Analytic des Probabilities, in 1813. However, it was soon realized that this definition cannot answer questions of so many problems. So for example, what is the probability that it will rain tomorrow? What is the probability that a child born today in a particular kind of family or with a particular ethnicity will get a height between, say, 5.5 feet to, say, 5 feet 7 inches kind of thing? Then what is the probability? How to calculate that? What is the probability that the amount of the food grain production next year will be more than this year? What is the probability that a person born today will live up to an age of, say, 60 to 65 kind of thing? None of these questions can be answered by the definition, which is the classical definition given by Laplace. So persons like Richard von Mises, etc., started thinking about this, and basically von Mises is credited to giving a formal statement of the empirical or relative frequency definition of the probability. That means you conduct the experiment a large number of times, and you look at the relative occurrence of the desired event in the total number of trials. And that is called the relative frequency definition. It was actually given in 1919. It's a book, it's a paper. Basically, it was published in the German journal Mathematical Gentrablatt. So it was published there. The axiomatic definition of probability, it was given by Kolmogorov, the Russian mathematician. In 1933, he published his famous book called Foundations of the Theory of Probability. Actually, even after this von Mises definition was given, the subject of probability was not considered to be substantially serious by, say, physicists or by mathematicians or by other people in chemistry or other sciences. They thought that it is some sort of loose kind of science, and therefore it did not get enough respect. So after 1900, there was a formalization of mathematics because of the Hilbert's program, where he thought that all mathematics can be formalized. And therefore, certain formal tools like the measure theory got developed. And Kolmogorov, because he was actually equally good in mathematics as well as in the probability, so he thought that he can use those tools. And he gave a formal formalization of the probability. So this is the axiomatic definition of probability that we teach to all the students currently. Of course, there is another school which I must mention here. It was led by the Bruno de Finiti. And he said that actually the probability should be used as a subjective thing. For example, like tomorrow, the election results are going to be out, and there are certain exit polls. Now you want to say, for example, in the say UP or in Punjab, that this party will get these many seats, or this seat will be won by this. So there you use, apart from the relative frequency, etc., because in such cases, the relative frequency does not arise because the election is happening for the first time, or you can say that those candidates are contesting for the first time under given situation. So you cannot apply. So there has to be some subjectivity involved there. So a school led by Bruno de Finiti, it was considered, they considered subjective probability. I would just like to mention the monumental contributions of some of these people, which are actually the part of the statistics studies now, the students who are doing BSc and MSc. So for example, for Kolmogorov, you look at he gave a model in the population genetics. So how the population grows, and of course it is also used in the wave propagation in physics. So these are the famous Fisher-Kolmogorov equations. In the stochastic process, we study the Kolmogorov's forward and backward equations. We study Chapman-Kolmogorov equations and Kolmogorov's inequality. We all know Chebyshev's inequality, which is there for the probability of an event. It is, so we write it into the terms of the random variable, and we look at that the random variable minus the mean lies in a certain range. Then it is bounded by something which is dependent upon the variance. In Kolmogorov's inequality, it is about the sum of the random variables. So it is a stronger thing actually. And then of course gave a lot of results in the laws of large numbers. So we call it Kolmogorov's strong law of large numbers. We call Kolmogorov's 0-1 law. That means the tail probability of a sequence is either 0 or 1. However, Kolmogorov made contributions to some other areas also, which are actually part of now the machine learning and data science. So one of the, so you can imagine the brilliance of his understanding of you can say science. So he did it in almost in 1950s. It is called Kolmogorov complexity. So algorithmic complexity theory, which is now one of the important parts of the computer science, it was also given by him. And another thing is the information theory, where he gave the measure of, so it is actually called Sinai entropy, Kolmogorov Sinai entropy. And I just now mentioned about the Bruno definity, that he gave a theory of subjective probability. He also introduced the concept of infinitely divisible probability distributions. Latter results have been developed by various statisticians for asymptotic behavior of sums of independent random variables. That is the weak and strong laws of large numbers, central limit theorems, law of iterated algorithm. So as students, all of you are doing all these things. You are studying the strong law, you are studying the central limit theorem, and so on. However, in the stochastic process, you deal with the dependent random variables. So if the random variables are dependent and then their distributions may also not be identical, in that case, what happens to these weak and strong laws? What happens to the central limit theorems? What happens to the law of iterated algorithm? So this is actually an active area of research. So recently, I also guided one research scholar in this area, and we have published some papers on the limit theorems for the sums of dependent and non-identical Bernoulli random variables. And there are a few publications that we got here. So it's an active research area. As students of statistics, you must know that if we violate the basic assumptions of the central limit theorem or the laws of large numbers, that is the identical distribution or independent distribution. So if they are non-identical or they are dependent, then for different type of dependencies, what should be the central limit theorem's statement, or what should be the statement of the laws of large numbers, whether you can prove them or not. So in these papers, we have actually proved those results here. Now let me talk a little bit about another aspect, because we are always talking about the data, data is coming from somewhere and so on. So what is data? So first phase in any problem is the identification of objectives and the relevant data. The data could be from primary sampling, it could be secondary data, or continuously evolving data, like in the COVID or in the, for example, every day a certain number of things is happening in the war. So this is continuously evolving data. Most of the government organizations, they collect primary data on its citizens. For example, expenditure on the health, education, food, luxuries, monthly income, employment status, etc. In India, we have National Sample Survey Organization and Central Statistical Organization. They have their headquarters in Delhi itself, and they do all this job. So for example, yesterday on the occasion of International Women's Day, you have seen the results of the 5th Family and Health Welfare Survey conducted by NSSO. And they have come up with the figures. I mean, of course, it's a sample survey, but based on that, they have concluded that the number of women, or you can say the female population in India, first time it has exceeded the male population. I mean, from the time of independence, the number of women in the population was less. That means the gender ratio, it was in the favor of men. In the last one also it was I think 991 in 2011 in the fourth family survey to 1000. That means on 1000 men you have 946 women or something. But yesterday they have given 1020 women per 1000 men. So first time the gender balance has come in favor of the females. So this National Sample Survey Organization and the Central Survey Organization, statistical organizations, their main job is to look at various kind of data from the whole country on so many type of things. So they collect the data on mining, manufacturing, output in the services, agricultural sectors, sales, consumer preferences, product prices, locations of the warehouses, factories, workers in the industries, their numbers, working hours, pay packages, workplace facilities, lifetime data. So for example, births and deaths, mortality due to various factors, distribution of population in different geographical zones. So again, I will talk about this one also, the distribution of population in geographical zones. So always, I think there is a narrative that is created that the population is increasing. Okay, the world population is increasing, the country's population is increasing, our particular state's population is increasing, and so on. However, if you ask a population statistician, that means a person who is dealing with the population statistics, then you will look at the correct picture based on different geographical areas, based on different regions in a country, and so on. For example, how many of you know that in India, is there any state where the population is actually decreasing? The answer is yes. In Kerala, the population has actually decreased over past 1 year or past 2-3 years, because there is a rate of population, that growth rate of population. If the you can say fertility rate or the birth rate is 2.1, it maintains the population at the current you can say numbers. If the birth rate is more than 2.1, then the population actually increases. If the birth rate is less than 2.1, the population starts decreasing. So in almost 100 countries of the world, the birth rate is actually much less than 2.1. It is somewhere, it is 1.3, 1.4. Most of the European countries and a lot of countries in the South America, etc., there the birth rate is much less than 2.1. There are a lot of countries where the birth rate is more than 2.1, but the number of such countries is reducing. For example, in our neighboring country like Bangladesh, it has become 2.1. So it has come to the stable state. Whereas if you look at the other side, that is the western frontier, like Pakistan, there the birth rate is 3.7. So the population is actually increasing. In Afghanistan, it is more, it is 4.8 or something. But of course, due to other other kind of calamities and other things like war kind of situation, their population is not increasing that much, and there is large scale immigration also. So I think as statisticians, we should not fall for any narratives which are given just like that by, say, people. You have to actually look at what is the real data and what conclusions can be drawn from there. We have nowadays data being analyzed in the sports. If you look at all the players, they analyze the data of the opposing teams and the job of the managers and the coaches and all those there. That is actually that thing. So what are their expertise? Then there is a health data, of course, which is a huge thing, like the proportion and prevalence of different diseases in the populations, expenditure on treatments, recovery rates, survival times, and so on. Other organizations, they use this data which is collected by the government, and it is called secondary. Why do they use secondary data? Because for every organization, it is not possible to collect the primary data, because it will use their resources and the time, etc. Because they have limited objectives. Any organization may, suppose there is an NGO and it is for the healthcare. So they may be looking at only the health data. Now they cannot go and do the complete health survey of all the people in India. So they can use the NSSO data, and they can make their policies that how they want to help the people in certain localities for certain diseases. So secondary data is helpful because it saves the times and resources for other organizations. So they can use their resources on devising strategies for their implementation. And as a statistics students, you must understand the difference between complete enumeration and sampling from the population. So, for example, this exit polls is actually based on sampling. That means the people who went for the voting, then out of the people coming out of the polling booths, some of the people are asked that what is their preference. The outcome of that is collected and it is published as the exit polls. The actual results are the complete enumeration, and that is why you will find many times the difference between exit polls and the election results. Sometimes wide discrepancies are there, and sometimes less discrepancies are there. The early methods were sampling from diverse populations like agriculture, biology, physics, in astronomy and cosmology, meteorology, etc. Experimental designs for agriculture and biological problems, and then development of statistical methods to analyze these have been developed by statisticians such as Carl Pearson, Gossett, that is a student, R.A. Fisher, Georgie Neyman, Egon Pearson, and P.C. Mahalanobis, the founder of Indian Statistical Institute. So these are some of the, you can say, primary statisticians. I mean, the ones who started the theory of statistics. So Carl Pearson is actually regarded as the first professional statistician. Actually, he established the first statistical laboratory in the University College London, and he founded the first statistics journal called Biometrica. All of you study the coefficient of correlation as a product one. So suppose you are given two data sets, xi, yi. So you have xi, yi as a bivariate thing. Then you consider sigma xi minus x bar into yi minus y bar divided by square root of sigma xi minus x bar square into square root of sigma yi minus y bar square. This basic measure as a product moment was first given by Carl Pearson, although it was used in some form earlier by Augustus Brevius and also by Francis Galton, but the formal definition and its properties, they were actually introduced by Carl Pearson. Carl Pearson is credited with the first use of a histogram for graphical representation of the data. Before that, in order to model any data that is given, that means whether it is coming from which distribution, etc., people had no idea that how to do that. So he is the first one who gave this idea of frequency classification, make a frequency distribution and then plot it and then join the midpoints by certain smooth curve. So that concept of frequency curve and histogram was given by Carl Pearson. And before Carl Pearson, actually the number of probability distribution which was in use is also very limited, because people only understood binomial distribution, Poisson distribution, and a normal distribution, but other distributions were not known. So he gave actually a wide family of continuous distributions. So this is called Pearsonian system of frequency curves. And actually development of the new probability models and studying their properties actually an active research area. So even I have worked with one of my students and we have published a paper on constructing a new distribution. It is a bivariate mixture of negative binomial distributions. Carl Pearson is also credited by giving the method of moments. Before that, actually only the Gaussian method of least squares was available for estimating the parameters, but that was based on the assumed model. But if you have any other distribution or any general thing, then how do you estimate? So Carl Pearson actually gave the method of moments. He also gave a measure of discrimination called a chi-distance. However, this chi-distance was refined much more by P.C. Mahalanobis in 1930s, which is called the Mahalanobis D square. And Carl Pearson also gave the chi-square test for the goodness of fit. That means if given data follows a certain distribution, so whether it is from a normal distribution or it is from a gamma distribution, so he gave a formal test procedure for this. That is called the chi-square test for goodness of it, and we teach to all these students in BSc and MSc programs. Another important statistician, it is actually nicknamed student, that is W.S. Gossett. Why he is important? Because he actually was not a statistician at all, or not even a mathematician. He was actually working in a brewery, that is a wine factory. And so in order to maximize the production and have some policies for the wine production, they wanted certain help, and he contacted Carl Pearson. But for testing a simple hypothesis like what we put in the modern terminology, that if we have a random sample from a normal distribution, a normal mu sigma square, and we want to test for the equality of the mean to a certain term, then the test statistic that is we use is square root and x bar minus mu naught by s, where x bar denotes the sample mean and s denotes the sample standard deviation. However, it was not understood that this has a t distribution. It was actually taken as a normal distribution by Carl Pearson and other people who were using it at that time. However, Gossett observed that this statement may not be correct, and so he approached Fisher, and Fisher actually gave a formal proof that it is actually a t distribution. And since the problem was actually raised by Gossett, so it was called students t distribution. And actually, they observed that for a small sample, t distribution is a different distribution than the normal distribution. If you have n greater than or equal to 30, then t distribution is approximately the same as standard normal distribution. So this actually motivated Fisher that we should consider methods which can be used even for small samples, because initially the data was genetic data or the data on agriculture, etc., or meteorology, where you had large scale data. That means lot of data was there. But the experiments which were being conducted in the industry, like Gossett himself was working in the wine industry. So you have a small data set. So maybe there are only 5 observations, or maybe only 10 observations are there. So then what to do? So in such cases, then Fisher thought that, okay, we should develop methods for that. And that is how the method of maximum likelihood estimation and other things came. So I'll just go very quickly to Fisher. So Fisher is actually, you can say, he is actually widely regarded as the father of modern statistics. So in 1922 and in 1925, he published 2 papers which are landmark papers. One is on the mathematical foundations of theoretical statistics in the journal Philosophical Transactions of Royal Society, and another one is the theory of statistical estimation, which was published in the Proceedings of Cambridge Philosophical Society. He also wrote some very popular books, that is the Statistical Methods for Research Workers and the Design of Experiments. And another book, of course, towards the end of his life, he wrote Statistical Methods and Scientific Inference. In these papers and the books, actually, he laid down all the modern statistical terminologies, like what is a consistent estimator, what is efficiency of an estimator. So all of this actually, the concept of sufficiency, the concept of Fisher information, the concept of likelihood function, the concept of maximum likelihood estimator, all of these fundamental ideas, they were actually given by Fisher. So he is actually, in a sense, academic forefather of all the statisticians. So I will just talk about the method of maximum likelihood estimation here, that it is one of the most significant concepts, actually, you can say, developed in the entire statistics. And actually, Fisher showed that for a small sample, it is superior to the method of moments. So that time, Arthur Eddington, he was an astrophysicist. So they were actually conducting experiments to verify whether the Einstein's theory of relativity is valid or not. So in 1919, there was a total solar eclipse, and people, astrophysicists, they collected the data, the telescopic data from the results of the solar eclipse, and that data they wanted to analyze. So naturally, certain estimation was involved. So Fisher actually said that, okay, if you use the maximum likelihood estimator in these problems, you will get better outcome. So this convinced and actually led to this one. So Fisher established that the maximum likelihood estimator has so many large sample properties like consistency, asymptotic unbiasedness, asymptotic efficiency, and asymptotic normality. And then again, I mean, of course, he also worked on the design of experiments and randomized block designs, the Latin square designs, the factorial designs, and so on. They were introduced by these people. I think I have come towards the end of my talk. Do I have another 5 minutes or so?
Yes, sir. Sure.
Okay, I'll take another just 5 minutes and then I'll wind up my this thing. I just wanted to show here that even these problems which were posed by Fisher, so some of the problems became famous problem. There is one problem like problem of a common mean of 2 or more normal populations with different and unknown variances. So a lot of contributions over the last 80 years have been made in this problem. But even then, me and my students, we have worked on some of these problems and we have published certain papers on this estimation of the common mean problem. This common mean problem arises in actually recovery of interblock information in the randomized block designs. So these are some of the papers that I have done with my students. So this theory of estimation and testing of hypothesis, it developed almost parallelly in 1920s, and the originators of them were Fisher and Georgi Neyman and E.S. Pearson. However, after 10-15 years, it was felt that there can be a unification of this theory, and this project was taken by Abraham Wald, who lived from 1902 to 1950. And when he unified this one, he gave a new theory called statistical decision theory, which is actually my research area. He introduced the concepts of minimaxity, admissibility, and proved basic complete class theorems, which established that any good decision rules are the base rules. He also introduced the sequential analysis, including the sequential probability ratio test, which we nowadays teach to the students when they are doing the course on testing of hypothesis. I have put the figure of another statistician, Charles Stein. So Charles Stein, actually, he gave the first two-stage procedure for estimating the mean and the variance in the normal distributions. And but he is then credited with giving a lot of new results. And one of them is actually that if you have more than one-dimensional problem, so if you have three-dimensional problem or a four-dimensional problem, then the usual maximum likelihood estimator can also be improved. This led to the construction of the James-Stein estimators and the so-called shrinkage estimators. So this is again a very active area of research, and I have implemented this in various research problems like estimation of the ordered means, in the estimation of hazard rates in several exponential populations, in the estimation of function of scale parameter in an exponential distribution, and in the scale parameters in the mixture models. We are able to do a lot of Stein rule type of estimation. There is another one which I just like to mention maybe before closing my talk. The other concept of information that was considered by Fisher. So we have this raw Kramer lower bound. We have where the lower bound of the variance of an unbiased estimator is actually the 1 by the Fisher's information measure. So this Fisher's information measure led to the estimation of information measure, and it is also related to the concept of entropy. So entropy measures, of course, nowadays in the signal processing, in the communication channels. So we have this Shannon's entropy, Renyi entropy, Kolmogorov-Sinai entropy, etc. So properties of the measures of entropy and inference. This is an important research problem. So we have also done some research work on these topics. So maybe I will stop at this point. There are so many other applications like the problem of discrimination and classification. Then there is a problem of, these are some of the topics which I have mentioned, the computer-oriented methods, empirical-based methods, James-Stein estimators, ridge regression, logistic regression, regression trees, Poisson regression, survival analysis, expectation maximization algorithm, bootstrap methods, parametric bootstrap, non-parametric bootstrap, bootstrap confidence intervals, cross-validation and estimates of prediction error, Markov chain methods, large-scale hypothesis testing, false discovery rates, least absolute shrinkage and selection operator, random forest and boosting, neural networks, deep learning, and so on. So there is a very, you can say, wide ground available to you. You have to go in any direction and take any path, but all the paths will lead to your specialization in statistics and applications to the data science and application to the real world situations. I think with this, I will like to close my talk. Thank you. If you have any questions, you can ask.
Thank you so much, sir. Thank you so much, sir, for briefing us about the rich history of the subject led by some pioneers. The concepts explained by you today holds immense value in the current times as data-driven is the future. I'm sure our students who have joined us today have learned a lot from you. Now I request anyone from the audience who have questions can put in the chat box or unmute themselves and ask.
Good morning, sir. So my doubt basically is that all the data analysts and data scientists now in the industry are usually guys who are good with their tech. So like they're software experts, and they don't have an in-depth knowledge of like statistics like what we graduates have. So learning statistics in depth and then actually competing with those data analysts, would learning statistics in depth give me an advantage over them? Or should I have just gone and learned that software and then gone into the industry?
No, just learning software will not be sufficient because you would not know that what method you have to apply. In that case, you would only be a servant. I mean, like your boss will say, okay, apply this software and get this outcome. Even the analysis of that you would not be able to do, and you will not be able to interpret that. So if you want to be in the leading position, in that case, you should have a proper knowledge of statistics, because if you know the software programming and other things, then you can use that appropriate methodology and then get the outcome. Otherwise, only your boss or your superior, he will say, okay, you do this. What is your name?
So Vignesh. My name is Vignesh.
Vignesh. So he will say, Vignesh, you do this and give me the result. So you will just apply the package. Some values will come. You will go and give the printout to him, and then he will use it. Whereas if you are knowing statistical methods, then you will do additional. And in that case, actually, you will be given superior responsibilities. Actually, one of my students, she did PhD in 2014-15, and now she is a data scientist in Walmart, posted in Delhi itself. But she is in a leading position, not a junior position. So that is because she knows statistics. So both the things are required. I mean, in order to become a leading data scientist, you should have a very good background of statistics. So I mean, statistical method should be known to you, and then of course you equip yourself with the software things, coding and other things. Okay, and also the little bit of modern methods like usage of the neural networks and this thing, because the deep learning and machine learning are the methods that you have to use now.
So I just want to ask another thing, like related to this question only. But like, sir, the guys who are like doing computer science and all, they have a really better background of like the modules and all that I use in data science. So like those guys,
no, they study. I mean, it's not that anybody knows everything, but if you want to excel in your area, then you have to study. So I mean, I know many of our students. I mean, they are from computer science, but they take up all our courses. Like I teach regression and time series, so they study my course. I teach the probability statistics. Right now, for example, in this semester, I am teaching statistical inference, and 90% of the students in my class, they are from computer science department. So I'm teaching them all this maximum likelihood estimation, sufficiency, the concept of information, the completeness, the Basu's theorem. I have taught all of them, and they are studying. I mean, my class is actually this semester consisting of almost all computer science students. So they do study, and I mean, like we are in the technical institute, so here we have every year we admit around 2,000 students, and out of 2,000 students, almost say 90% of the students, they actually do statistics courses. So because my course, they are doing all of them. Like last semester, I had 1,400 students in my class. So so it's not that they are doing computer science, so then they won't do statistics. They are actually doing both. And not only the students from computer science, the students from mechanical engineering, the students from mining, they are also learning both. They are learning computer science as well as they are learning statistics. So the future is that actually you should have both skills. Being weak in any skill, it will not help you. Then you will be in a subsidiary position only, not in a superior position.
Thank you, sir. That clears matter.
Thank you so much, sir, for answering our questions. Now I would like to move to the vote of thanks. For this, I would like to call upon our senior faculty member, Mr. Akash Vashne, to present the vote of thanks. Over to you, sir.
Yeah, thank you, Shruti. We are very much delighted, sir, Sumesh sir, for giving us a talk on the subject history and recent works in statistics and data science. And as all of us like knowing that he excellently connected the use of statistics in understanding and controlling corona epidemics recently. So that was a great use of statistics. And as far as the subject title is concerned related to history, he guided us, and he's told us that data collection was there from very long back. And it origination and data development and everything is a connection of all the things were the explanation given by him was excellent. And and as of all of us know, role of uncertainty in different subjects, areas like chemistry, biology, finance, economics, weather, food grain production, everywhere we are going to apply statistics. And now from a non-exact science to it has transformed to a very much exact science. So we are very much delighted, sir, having your talk, and statistics department is really thankful to you for giving us a great talk today. Thank you, sir.
Yeah, thank you. Thanks. So I will disconnect now. Thank you very much.
Thank you. Thank you so much, Professor Sumesh Kumar, sir, for taking time out from your busy schedule and addressing the gathering with your wisdom and knowledge. We are very delighted that you have joined us today and started a simulation event with such an inspiring talk. Thank you so much, sir.
Okay.
Thank you, sir.
एक मिनट